In this lesson, we'll take a look at some of the properties of probability that can be derived from the axioms that we studied earlier. In particular, we'll talk about disjoint events, and then we'll talk about the addition rule for disjoint events, as well as the generic addition rule. And then we'll talk a little bit about subsets and complements. And finally, we'll take a look at a theorem about the upper limit on the value for a probability. Two events are said to be disjoint, or also often said to be mutually exclusive, those are equivalent terms, if they have no outcomes in common. So for instance, we roll our six-sided die. The event you roll a prime number includes the outcomes 2, 3, and 5. The event that you roll a perfect number includes the outcome 6. And so A and B here are disjoint. They have no outcomes in common. If we wish to know what the probability is that at least one of our events occurs, A or B, and we express that as the probability of A union B, then for disjoint events we just add the probabilities of the individual events. So again, for our six-sided die, the probability that we roll a prime number is 3 out of 6. The probability that we roll a perfect number is 1 out of 6, and so we add those together to get 4 out of 6, or 2/3, for the probability that either we roll a prime or a perfect number. We can extend this to an arbitrarily large collection of events, including an infinite number of events. So we'd say the probability that at least one of these events occurs is equal to the sum of the probabilities of the individual events. Notice that we can only do this because they are disjoint events. If they're not disjoint events, we run into some trouble where we double count a lot of things. Note in this case that n can be either a finite case or an infinite case. In the book, Debreu uses the infinite case to illustrate the rule. But the rule doesn't change between the finite and the infinite cases. Okay, so I said we could get into a little bit of trouble if we don't have disjoint events. So if we're looking at two events A and B that are arbitrary, we don't know whether they're disjoint, we need to say the probability that at least one of the events A or B occurs is equal to the sum of the two probabilities of the events minus the probability that both occur. And the reason for that is that when we count up all of the outcomes in A, some of them are also in B. And then when we count up all of the outcomes in B, some of them are also in A. So there's overlap. If we add those two probabilities, some of that probability is being counted twice, and so we need to subtract it off once. Just a note on notation in Debreu's book, he uses the probability of AB to indicate the probability that both A and B occur. That's more commonly done as the probability of A intersection B, but his notation is a little bit more concise. Okay, so we talk about subsets now. An event A is a subset of an event B if every single outcome in A is also listed in B. And the notation for that will be A contained within B. So as an example, the vowels are a subset of the entire alphabet. So every vowel, A, E, I, O, or U, is in the list of all of the letters of the alphabet. A probability then of a subset is always less than or equal to the probability of the event that it's a subset of. So if A is a subset of B, then the probability of A has to be less than or equal to the probability of B. And that follows because the probability of all of the outcomes in A are non-negative. The probability of all of the outcomes in B are non-negative. And so if you add them all up, there are additional outcomes in B, possibly, right? If A equals B, it's still considered a subset. But if there are extra outcomes in B, those probabilities are all non-negative, so you can certainly never decrease that sum. And so it'll be a larger number or possibly just equal to the same number. A complement of an event A is just a list of all of the outcomes not included in A. So, for example, if you roll that six-sided die and the event we're interested in A is you roll less than 3, that would include 1 and 2. So the complement then would include all of the other outcomes, 3, 4, 5, and 6. The probability of a complement is going to equal 1 minus the probability of A. And we know that the probability that some outcome occurs is equal to 1, and therefore, if we've got these two disjoint sets, we know that the probability of A complement plus the probability of A has to equal 1, and so the probability of A complement equals 1 minus the probability of A. This is an extremely useful trick, and we're going to come back to it time and again. Finally, one proposition that's not covered in this chapter of Debreu For any event A, the probability of A has to be less than or equal to 1. You'll notice in the axioms, all we said about it was that it couldn't be negative. It had to be a non-negative value. We didn't say that it couldn't, for instance, be 2 or 5 or 20. So we know from probability property number 2 that the probability of a complement is equal to 1 minus the probability of A. So assume for a second that the probability of A is greater than 1. For instance, maybe it's 2. Well, then what would happen is the probability of A complement would be 1 minus that number greater than 1, and that would have to be a negative number, and that's not allowed from our probability axioms. Our axiom says that all probabilities have to be either greater than or equal to 0. So since this would lead to a negative probability assignment for that complement, it can't be the case that the probability of A is greater than 1, and so it must be less than or equal to 1. And so when you say probability of A must be non-negative and it now must be less than or equal to 1, this is why we can say all probabilities are between 0 and 1.